We're going to take a closer look at inverse functions as opposed to relations, because inverse functions are actually more useful for our purposes. First of all, some notation. Now, it's not meaning to the power of -1, but we use that -1 superscript as a notation for inverse functions. Now, the nice thing about the composite function of a function and its inverse, because you're sending everything back, then you should end up with x, because everything should go back. So just to show that, here's function x minus 2, x plus 2, and if I was to find its inverse, I'd swap the x and the y's around. I'll make y the subject, a little bit of algebra there, but eventually we get it. So if I substitute in, which one did I do first? The function into that inverse. So everywhere I see x, I'm replacing with 2x plus 2 on 1 minus x. Let's play with the algebra here. We'll multiply everything by x plus 2 to get rid of the denominators. Tidy it all up. Yes, indeed, we get x. Let's go the other way just to show it works that way as well. If I substitute the inverse into the original function itself, this time I'll multiply everything by 1 minus x, and again we end up with x. And that's what we would expect to happen, because it was sending everything back to the independent variable. Okay, domain and range then. As we mentioned the other day with inverse relations, the x and the y values are basically swapping around. So if the point AB is on the original function, then the point BA should end up on the inverse function. So the domain of the original curve will become the range of the inverse, and the other way around is true too. The range of the original function becomes the domain of the inverse. So that's still all the same. So let's have a look at this one. Y equals e to the power of x, our basic exponential. The domain of that is all real x. The range, however, is y is greater than 0. Now, the inverse function of the exponential is the logarithm. And that's how we undo the exponentials. We log both sides. So it would be y equals log x. Now, the domain of y equals log x, you may recall, is x is greater than 0. And the range is all real y. And if we were to draw it, there it is, a reflection in the line y equals x. Again, what we were expecting, because that's what we said inverses do. But I guess more importantly for our purposes here, notice how the domain and the range have swapped between the function and its inverse. Okay. Problem is, most functions will not have an inverse. Remember, it's only the one-to-one functions that will have one. But we really need to have inverses for all sorts of functions. So we need to restrict the domain to make it a one-to-one function. What we basically do is you want to get a piece of the graph that is continually increasing or decreasing. Because if it's continually increasing or continually decreasing, that means it doesn't turn and come back. Because if it did turn and come back, bang, that's when it's going to fail that horizontal line test. So we need to grab a piece continually increasing or continually decreasing. So let's have a look at our parabola, which we know does not have an inverse function because it fails the horizontal line test. So the domain at this stage is all real x and the range is y is greater than or equal to 0. So it's no good, we can't find an inverse. We need to restrict our domain. So I want to grab a piece of this parabola. I've chosen x is greater than or equal to 0. So I start at 0 and then keep going. I'll get something that's continually increasing. I suppose you could have gone x is less than or equal to 0 as well. That would have worked. We tend to go with positives if we have to make that choice. Well, you don't have to, but that's the way we tend to go. The range doesn't change. I managed to get the complete range by restricting our domain to that. So the inverse function, notice it's no longer plus or minus the square root of x, because that would give us ambiguity. We said it had to be unique. But by restricting my domain, I no longer have plus or minus the square root of x. I've just got the positive square root. I've written it in index notation, x to the power of a half. So the domain of our new function is x is greater than or equal to 0, and the range is also y is greater than or equal to 0. And if we were to draw it, there it is, our sideways parabola, well, the top half of the sideways parabola. This does give us another way of finding range. You see, if I know that the range of the inverse is the domain of the function and vice versa, if I want to find the range of something, I could find the domain of the inverse. Because sometimes people find domains easier to find than ranges. So the domain of the inverse function will be the range of the original one. So again, y equals x squared. I will swap the x and the y's around. Notice I've used capital X and capital Y so I don't confuse myself here. This is referring to my inverse function, the new function. So that will get me y equals the square root of x. Now the domain of this new function is x is greater than or equal to 0. Therefore, the range of the original function must have been y is greater than or equal to 0. Now, I'm not suggesting that you would use this method for that particular one. One would hopefully be able to look at the parabola and just get it. But it illustrates how you could use inverse functions to do that. Y equals x squared plus 3. Again, I'll swap the x and the y's around, but so I don't confuse myself, I'll make them capital so I know which one I'm talking about. That becomes y equals the square root of x minus 3. So the domain of the new function, or the inverse function, is x is greater than or equal to 3. Therefore, the range of the original one must have been y is greater than or equal to 3. Y equals the absolute value of x plus 2 minus 5. All right, so we'll swap the x and the y's around. We'll make y the subject. So x plus 5 is the absolute value of y plus 2. That means x plus 5 must have been greater than or equal to 0, because it's an absolute value function. So the domain of the new function is x is greater than or equal to negative 5. Therefore, the range of the original function was y is greater than or equal to negative 5. Let's do our semicircle, but let's pretend we don't know it's our semicircle. So y is the square root of 4 minus x squared. Swap the x and the y's. If I make y the subject of that, I actually get y equals 4 minus x squared. The same function. That's interesting. So the domain of the new function is x is in between minus 2 and 2. But hang on a sec. We know in the original one, y was greater than or equal to 0. So you've got to be careful if you're using this method. So I can't simply say the range of the original one was between minus 2 and 2, because we had that added restriction with this one that, oh, hang on, y has to end up being a positive number because it's the positive square root. So it must only be between 0 and 2 for that one. So it's not always as clear cut as you would like, this method. Y equals x plus 7 on x plus 4. Swap the x and the y's around. Eventually I get y is 7 minus 4x on x minus 1. Eventually. Well, that domain would be all real x except x is equal to 1. Therefore, the range of the original function is all real y except y is equal to 1. And yes, indeed, that does turn out to be the range of that original function. All right, so that's maybe a use for inverse functions you could have.